Our project is neodymium magnets in speakers.
One of the applications of neodymium magnets is in speakers. They are used as a permanent magnet of which a coil is wrapped around. This coil transmits an electric signal alternating to cause a vibration in the magnet, and that vibration creates sound. This is just one of the applications of neodymium magnets.
Neodymium magnets are excellent permanent magnets because they have a high residual magnetism, which means that without the magnetic field, they're still very strong, and their moderate coercivity means they're hard magnets. Because neodymium magnets have a higher energy product in a normal temperature range, they can be more compact and more lightweight than conventional ferrite magnets.
So neodymium magnets have tetragonal structure, as you can see in the picture. Within this tetragonal structure, we have trigonal prism structures as shown in the picture here. We have neodymium atoms surrounding the boron atom, and we have iron atoms at the top and the bottom. These boron atoms binds the layers covalently, which gives this magnet a very high durability and strength. This structure leads to magnetocrystalline anisotropy, which helps to increase the magnetism and coercivity of this magnet.
The magnets are created with two main ways. First is melt spinning, and then another one is powder metallurgy. So for melt spinning, first all of the component metals are melted and deposited on a spinning copper disc at high speed. This creates ribbons, and the ribbons are ground and consolidated in three different ways. First, they can be bonded with epoxy, or they can be put in a vessel and hot pressed, or they can be die upset, which is after hot pressing, they take the product from hot pressing, put it in another die, and then press it again with different dimensions. This creates even a more high energy product. So bonding is the least high energy and die upsetting is the highest energy. The second way to do it is powder metallurgy. This is the most common way to do it with commercial magnets. So the first way is, the first step is the components are induction melted together. Then they are crushed, milled, and pulverized, a lot like melt spinning. Then they're aligned in a magnetic field. Then they are pressed together, similar in these three ways. And then they are sintered, which is putting it in the hot gas, and this increases the magnetic potential. Neodymium magnets are constantly evolving. We're moving from a sintered magnet to a bonded one just because they're more precise and they're cheaper to manufacture. And we're constantly evolving the composition of the magnets themselves by doping with different impurities.